Welcome to section 5.3, Poisson probability distribution. In this lesson, we'll focus on modeling rare events, things that don't happen very often, but can be counted over fixed intervals of time or space. The Poisson distribution helps us answer questions like, how many customers might show up in an hour? It's especially useful in fields like operations, logistics, and insurance. The Poisson distribution models how many times something happens in a fixed interval, like time, distance, or space, when the events are rare, random, and independent. It's used all the time in real-world problem solving, and especially in situations where you're not asking whether something happens, but how many times it does. Let's ground this in your life as a college student. Imagine you're working at the campus coffee shop, and on average, 4 customers walk in every 10 minutes. It's not exactly like clockwork. Some intervals are busier, others are quiet. But over time, 4 per 10 minutes is a stable average. Using the Poisson distribution, you can calculate things like, what's the chance no one shows up in the next 10 minutes? Or how likely are exactly 3 orders to be placed? Or how often should we expect a rush of 6 or more? This isn't just useful for scheduling. It can be applied to study room bookings, maintenance requests in a dorm, or even how many people message your student organizations each week. If you can count it and it happens randomly over time or space, Poisson is probably in play. Let's talk about when Poisson is the right tool for the job. Well, if you're counting how many times an event occurs, the events happen independently, one doesn't influence the next, and they occur at a constant average rate over time or space. For example, you might count how many texts a student receives per hour, or how often gamma ray bursts hit a detector. In the Marvel universe, it could be how many Asgardian relics are unearthed per excavation site. If we know the rate, Poisson lets us compute the chance of observing a particular count, whether that's 0, 1, or 10. Here's the formula for the Poisson probability. So our probability of x being equal to k is mu, the mean, to the k, e to the negative mu over k factorial. Let's break that down. Mu is the average number of events in the interval. X equals k is the actual number of events we're calculating the probability for. E is Euler's number. That's a constant, about 2.71828, so on. It's kind of like pi. It's a number we use frequently in math. K factorial is the factorial of x, the product of all the positive integers up to k. The formula might look intimidating, but once you plug in mu and k, calculators or Excel can handle it quickly. Let's look at a practical example. A tech support help, let's suppose a tech support help desk gets an average of 3 calls per hour. What's the probability they get exactly 2 calls in a given hour? Well, we plug into the formula, right? This is our average. Mu would be 3. We want to know exactly 2 calls. That's our K. So we're plugging into that formula that we just found, right? The probability of K being mu to the K, e to the negative mu. That's a mu over K factorial. So 3 squared e to the negative 3 over 2 factorial. So if we plug that in, that's about 0.224. All right, so how do we plug that in? Well, there are a couple of ways we can plug that in. And I'm going to go to Excel here to show you. Okay, we're doing 2 cols in an hour, right? So we're plugging into 3 squared. So we could do 3 squared times e to the power -3, and then divide all that by 2 factorial. Oh, it doesn't like e. I think maybe it's exp -3. What? Oh, it doesn't like 2 factorial? Okay, well then we have to do 2 times 1, right? That's what 2 factorial is. And there's our 0.224, right? What we found here. Now, there's another way we could do it. This is the Poisson distribution. So our x here, x was 2, and the mean is 3. So we want to go 2, 3, we don't want this to be cumulative, so we put false. And there's the same value, 0.224. One unique feature of the Poisson distribution is that the mean and variance are equal. Both depend entirely on mu. The mean is just mu, and the standard deviation is the square root of mu. If mu equals 5 events per hour, then the standard deviation is the square root of 5. This tells us how much variability we can expect from 1 hour to the next. If mu is large, the standard deviation will be as well, meaning counts could fluctuate widely. Sometimes we want the probability of at most k events. That's what we called a cumulative probability, the sum of the probabilities for 0 up to k. For example, if I want to find the probability that x is less than or equal to 3, that would be the sum of the probability of 0 plus the probability of 1 plus probability of 2 plus the probability of 3. This is where technology really helps. Calculators, Excel, or online tools can compute these quickly. You can also use the complement rule, that the probability that x is greater than or equal to k is 1 minus the probability it's less than or equal to k minus 1. This is useful when you want to know the chance of a high number of events occurring, like multiple sensor failures or heroic rescues in a day. Let's apply what we've learned. Hulk averages 1.5 rage bursts per day. Small outbursts, nothing too dramatic. What's the probability that he has 3 or fewer in a day? So we are looking for the probability that x is less than or equal to 3. So using the Poisson model with mu equal to 1.5, we would plug in and calculate the probability at 0 plus the probability at 1 plus probability at 2 plus probability of 3. And we're going to get 0.934. We could also do it a lot faster using the cumulative probability function in Excel. So again, if I get out of here, get out of here. And let's go back to Excel again. What do we have? We have our k is 3 and our mu is 1.5. So we would go Poisson. The k was, I already forgot, 3. Yeah, 3. 3, and then the mean is 1.5. And this time we do want the cumulative probability, and there it is, the exact same thing we saw on the slide, 0.934. So there's about a 93.4% chance of Hulk having 3 or fewer incidents. That kind of insight might help Bruce Banner plan a light training day. Sometimes calculating exact binomial probabilities is tough, especially if n is large and p is small. That's when we use the Poisson approximation. The rule of thumb is if n is large, p is small, and mu, which is n times p, is less than 7, then you can approximate the binomial with a Poisson distribution using mu equals np. This shortcut saves time, especially in older or manual calculations. Just remember that it's only valid under the right conditions. Let's say 300 Avengers attempt to lift Thor's hammer, Mjolnir. Each has a 1% chance of succeeding, and we assume independence. That's a binomial setup with n equals 300 p is my 0.01, and mu would be n times p, so 3. Because mu is small and p is low, we can use a Poisson model with mu equals 3. If we wanted to find the probability that no one succeeds, the probability of 0 would be 3 to the power 0, e to the negative 3, over 0 factorial. By the way, remember that anything to the power of 0 other than 0 is a 1, and 0 factorial is a 1. So this is really just e to the negative 3. That's about 0.0498. So there's about a 5% chance that none of the 300 Avengers lift the hammer. Not even Spider-Man. And tough crowd. All right, to wrap up. Use Poisson when modeling counts of events in a fixed interval of time or space. It's ideal for rare independent events like emergency calls, radioactive emissions, or alien sightings. The distribution has one parameter, mu, which controls both the mean and the variance. The Poisson approximation is helpful when binomial calculations are impractical. Whether you're scheduling tech support, studying background radiation, or forecasting hero landings, the Poisson distribution is a key tool in your statistical toolkit.